I don't have a huge list of speakers or anything today, but I do have Randy contacted me and let me know that he has a talk on HD 110067, and we also have Lauri that has a few things she wants to speak to, and I might show a couple pictures at the end. So do you want to kick us off, Randy?
No, because I haven't logged in yet.
Okay, well, we'll give you a few moments.
So speak among yourselves.
Okay. That works. Oh, and there's a lava lamp. That looks like a real lava lamp, though. That's not some filter that he's playing with. But he's talking, and we didn't get to hear his commentary.
I've always wanted a lava lamp, so I finally talked someone into getting one for me.
Nice. You've finally gotten into the 70s.
That's right, yes. I'm a little behind on most things.
Just 50 years. Yeah. Isn't that sad? That the 70s are 50 years ago. Sorry. That's really sad.
It's simply not true, Lauri. We'll start a rumor and deny it. So do so.
Yeah, just total denial.
Sorry.
Would you like me to speak now?
Please speak, yes.
Oh, well, there we go. I will share the screen.
Of course, you'll need to move us again.
And Lordy, I gotta go here. We'll get there. Sorry, I didn't think I was going to be first thing, so I'd have lots of time. So, yes, we are going to talk about HD 110067. HD stands for Henry Draper, who was one of the first astrophotographers in the 19th century, and he died, as people do. And his wife, Mary, was very wealthy, and she decided to give, what was his name, Pickering, lots of money to pay for all these female computers to go through the Harvard photography collection, as long as they called the catalog after her husband. So it really should be MD because it was Mary Draper's idea. But this was the 110,000th star. And according to an article that I just read, it could become the most interesting star in the galaxy. Okay, let's go and see why. So on Friday morning, as I'm reading the Globe, on the front page of the Globe is an astronomy article. We're going to learn a lot. Discovery of 6-planet solar system with mathematically remarkable orbit wows astronomers. And let me tell you, it wowed me. So I spent probably too much time this weekend learning about it, but it was it's a delight, this story. So you go to the original article. It was published Thursday morning in Nature, and lots of authors. And then, the second page, there's over 150 authors. And then you look at their institutions, there's 5 pages before you even get to the beginning of the article. So let's talk about HD 110067. It's in Coma Berenices. Can somebody correct me on the spelling? Berenices. On the pronouncing?
Berenices.
Berenices. It's a constellation I know nothing about, but it's between 2 that I love, Leo and Boötes. And I think it's just there as a place filler because there are no stars of any note in it. except for 110067, of
A
course.
whole whack of galaxies.
There's a whole whack of galaxies.
Right in between those two.
Okay, good. So the star itself, magnitude 9, you know, as far as the exoplanet people are concerned, this is super bright. And I think it's the brightest exoplanet star, or at least one with 6 planets. Its main sequence, it's a plain hydrogen burning, it's spectral type K. And I just need to tell you, my favorite mnemonic now is, let's get it right, it is bad astronomers always forget generally known mnemonics. Okay, for people who want to know the sequence of stars from the hottest to the coolest, that's the best mnemonic. It's much better than the original one that those fine women in Harvard came up with. Anyway, Sun is a G. This is a K that's just a bit cooler. And if you take a look at the temperature, it's about 500 degrees cooler than the Sun. It's 0.8 of the mass of the Sun, 0.8 of the radius of the Sun. It's just a baby sun. The important thing I also want you to see on this list is it has a TOI number, and that means it's TESS object of interest. So it's, you know, there's not a lot of them. There's under 2,000. I don't know how many there are, but this one was an early TESS object of interest. So let's go to figure 1 of the paper. And it's rather complicated, so we're going to pull it into pieces. So let's start with this. So TESS is the Transiting Exoplanet Survey Satellite. As you can see, it has 4 cameras, and it sits on a sector, they call this, for about a month, and then it moves. And part of the time, the Earth and the Moon get in the way, so you don't get data for the whole month. This is days at the bottom. So this is 1,930 days since the beginning of the mission. And the vertical, so day, this is time in the horizontal, and vertical, it is the brightness of the star in parts per thousand. Okay, so 1 part per thousand is, you know, around here. And so we're really seeing parts per million differences in the brightness. And every once in a while, there's this little dip, and that is a transit. That is a planet going in front of the star. Just imagine, like this, you can do it now in 2020, but this was not something that people could do even, I think, 15 years ago. This is really like current stuff. And at the time they said maybe there's a planet with a 5-day orbit, but you know, you can't really tell too much. But it definitely made it a TESS object of interest. They knew they had something cool here. And in particular, a postdoc in Chicago named Raphael Luke got his teeth into this. And he's the first author of the paper. So 2 years later, the first one had a measurement cadence of a minute, and then in the second time they looked at the same part of the sky, it was every 20 seconds they took a measurement. So that's why there's so many more dots here in the second time series than in the first. And I want you to know that the straight line is the same data as the first line, but it's been detrended. It's been made so that the star is constant, and it just helps you see better where the dips are, okay? And with this, they could see that there was planet B. Now, you got to understand with exoplanets, I remember asking one of our speakers about this, and A is the star itself. So B is the innermost planet, or is it the first discovered planet? I think it's the first discovered planet. C is the second, D is the third, etc. Okay, in this case, B is also the innermost. And they, on the basis of this data, had it to 3 decimal places. Okay, so what is that? That's going to be to, minutes. They could get the period. So 9 days, and C had 14 days. And then there were a bunch of other unidentified transits. They knew it was a complicated system. And you got to understand, this is really cool. We're looking at that star, and these planets are in a planetary system, which is exactly in the plane of the star. Like you're looking at the star, and the planets are eclipsing it or transiting it. It's most, because these planetary systems will be in all directions, right? But this one happens to be spot on in the right direction. Great. Okay. Anyway, they took out their calculators and said, whoo, look at that. The planet C goes around the star twice in almost exactly the same amount of time that planet B takes 3 orbits. It is in orbital resonance. So the famous one that any of us can see with our telescopes, and Nathan and I had a really lovely little 2-month experiment looking at the Galilean moons around Jupiter. Very easy to see these with even like a 5-centimeter refractor. Anyway, the 3 innermost moons of Jupiter have periods with ratios 1, 2, and 4. So you can see every time they change color here, you've got these close approaches. And really, they're the only ones that are important, because if one of the planets is lagging behind, it gets a little zets to pull it forward. And if it gets a bit ahead, it gets a little bit of a pull back. And so these planets are all arranged in this really, really stable configuration that can last for billions of years. And it turns out the exoplanets, lots and lots of them, are in orbital resonance. Not always 1 to 2. You could also have 2 to 3, 3 to 4, 4 to 5. Those are the most common. Okay, so the people studying this planetary system then got time on Cheops. And Cheops only looks at 1 star at a time. And so they said, if we want to see what these other transits are, let's make a hairy eyeball hypothesis that they're also in orbital resonance. And so they said, these are the times we would like you to turn this telescope on this particular star. And I think if I were picking up this data, I would feel pretty frustrated. Like, they got B. Well, they already know the period of B. So that's not very interesting. And this one's important. They got D. And the other thing is they got rid of a whole bunch of hypotheses of the other ones. By doing this set of data, they firmed up the B, C, and D. And so with that, they were able to say that D had a period 3/2 times C. C has the period 3/2 times D. And they knew that it was likely that E and F were going, or was it F and G, were going to be 4/3 times. And if so, then the data should be hiding in this zone here when the Earth and the Moon were in the way, or made too much noise. And so this is my favorite part of the whole story, and I'm going to read this all out to you. This was from, so the article is in Nature. This was the report in Science. You see 11 a.m. on November 29. So they had this article, and as soon as the embargo came off the Nature paper, they put this to press. So I'm going to read this out. This amount of supposition and theory might not convince everyone, but the team had a stroke of luck. A team at NASA's Ames Research Center had devised a new way to reprocess test data that is normally discarded as too noisy. And it's too noisy because of the sun and the Earth and the moon making too much scatter inside the telescope. Luke's team, that's Raphael Luke, the postdoc in Chicago, asked the Ames team to look in the discarded data from the 2020 observations for the predicted transits of the 5th and 6th planets. There was gold, Luke says. It was truly unbelievable. The transit of the 5th planet was spot on, and the predicted period of the 6th was off by only 20 minutes, despite being extrapolated from a single transit orbit observed 2 years later with a period derived by pure theory. So I gotta say, as a scientist, the best feeling in the world is when you know something that nobody else in the world knows. And it's one of the highs of life. And I wish it on everybody. You only get it a few times in a career. And this fellow certainly has it here. Okay, so why did I show this picture again? I don't know.
It's got the noisy data.
Anyway, you can see that you have at least 3 transits of every planet except for F. You only have 2. And if you only have 2, you don't really know if you have a planet or whether it's 2 separate planets that came by. You need to have at least 3 to have any confidence. So this team figured out that planet F, if it has the period they are expecting, should be seen on May 23rd, 2022, but there was no place on Earth where they could see both the ingress and the egress. They could see it going in and going out. And so they contacted their friends. I love this part of it. That's why there's 150 authors. So in a couple of observatories in Spain, that's these, the first 4 are from one place, and then this green one here is another. And then there's a whole set of like 1 meter telescopes in Paranal in Chile. And then a couple in Spain. No, Spain was the first one. These are in North America. These were in Arizona and in Baja California. So you're getting lots of different time zones. And again, these are in units of parts per thousand, and they got it. They predicted where it would be, and here it is. It's about 8 hours that it takes for this planet to cross the face of this star, and it is observable. You know, with a lot of modeling, and you know, the data is pretty noisy, but they could see through it because they had all these instruments, and because they're very clever. So now they have the periods of the 6 planets. They don't have the masses yet, so they got a couple of radio telescopes in Spain to look at it for, what is that, 300 days or so. So, you know, better part of a year. And by looking at the radial velocity, looking at the Doppler shift of the central star, then they can work out what the masses of the planets are. And again, huge amount of modeling. It's not easy, but they were able to pull out all of these parameters of the 6 planets. So you see here we have the list of the important parameters, and then we go B, C, D, up to G. Okay, you see that? And the little sniggle there for E and for G is because there is some model dependency here, but the other ones are direct measurements. And so let's go through this table. First of all, the period in days. So 9, 14, 20, 31, 41, 54. So I divided all of those by the first one. And then I hate to say that it was by a lot of trial and error, but I realized that if you then multiply that by 8, these all come out to nice integers. So let's just say it's 8 days for the first planet, then the second would be 12. The third would be 18 days. The fourth is 27 days. And those are all that 3/2 ratio. And then for whatever reason, the fifth planet has a 4/3 ratio, and the sixth planet is a 4/3 ratio. And they're all good to about 1%, maybe a bit better than 1%, which is pretty awesome. Okay. So this was in the Scientific American story that came out today. For some reason, they say if planet C goes around 360 degrees, so 1 year of planet C, in that time, planet B goes around 1.5 times, and the other planets go around slower, 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 but it's all in very nice, easy ratios. It turns out that for G to go around 1 year is 6 years for B. Okay. The masses are all quite a bit larger than the Earth, but less than Neptune. These are called sub-Neptunes. And it's interesting, there's nothing in our solar system between Earth and Neptune. Earth is the largest rocky planet, Neptune is the smallest icy planet, and there was all sorts of theories about why there was nothing in between. Turns out that these are the most common exoplanets that are seen out there. And astronomers would like to understand more about them. Their sizes. So the radius of the planet as a multiple of the radius of the Earth are all around 2. Okay, so they're not huge planets, but they're not like anything in our solar system. And they're all kind of the same, which is also, I think, kind of freaky. The other thing is they all would fit within the orbit of Mercury. Okay, all 6 of these planets are really close in. They're big, they're sub-Neptune, but they're bigger than Earth, and they would all be closer than Mercury is to our sun. Remarkable. And then for the people who actually care about whether there's somebody there training their telescopes on us, they're too hot. So the innermost one is 800 Kelvin, but even the outermost, 440 Kelvin, that's like 170 degrees Celsius. I don't think there's anybody living there.
Not water-based.
Not that look like us. So this again was from the Science article. It's a delightful system, says astronomer Carol Haswell of the Open University, who was not involved in the study, one of the few, published today in Nature. The planets' orbits are all tighter than Mercury's, but if further observations find more planets in the star's habitable zone where liquid water can exist, Haswell says, then it could become the most interesting star in the galaxy. And I'll close with this pretty picture of the interactions between the planets, and thank you.
Very nice. Very interesting. Any questions for Randy?
Yeah, Randy, how far away was that?
105 light years. Good question. 32 parsecs.
Thank you.
So it's considered really close.
All those orbits must be almost perfectly circular.
They don't have estimates of the eccentricities, but yes.
Yeah.
So Randy, this is astonishing. Now, the planet's mass does not, it doesn't have anything to do with its period, just its position does. Is that true?
Okay. You use Kepler's laws.
Yeah, there's 3 of them. I just looked them up.
And So in proportion, the third law is that the period goes as the 3/2 power of the distance, something like that. But then you use Newton's law of gravity, and you can work out the masses. And oh boy, it's been a while, but I know that the thing that astronomers love with binary stars are eclipsing visual binaries. So ones that you can actually separate, but also one goes in front of the other so you can get the light curve. And then you can work out all sorts of things like the masses of the planets, of the stars. And it's the same thing with these planetary systems. So once you have the radial velocities and the relative distances and the periods, then you can work out the masses. But if you just have the periods, but you don't get to measure the radial velocity, then you just know the proportions. You don't actually get their mass.
So you're saying that it does make, like, I'm having here not believing that this is truly incredible. If the mass makes a difference to where the planet is and what its period is, to have exactly those ratios is almost unbelievable.
Well, that's because they start from this gas nebula and they make these little vortices and they form into their planets. And then there is this force that will, if one is going a bit too fast to be in resonance, it'll slow it down, and the other way. So like Mercury is in a 3/2 resonance with its day. So every year at perihelion, when Mercury is closest to the sun, it's either pointing this way or it's pointing the other way, because it's a bit of a football. It's elongated. And so it's either one side is pointing towards the sun when it's closest to the sun, or the other way. Okay, can you see my hands? I don't know whether I'm too small. And so you get these resonances, because if you're not right on that ratio, then there's a gravitational tug. So it's not actually a coincidence. What happens though is then another star comes by or something happens and it perturbs the system and you get out of whack. And so one of the things that the exobiologists and the other people that are keen on these things are saying is this planetary system hasn't been perturbed for billions of years. And this star, they figure, is about 8 billion years old. It's about twice as old as our sun. And the system has been sitting there unattacked. Which is, yeah, it's quite something. That's a good, that's half the universe.
Lauri, did you have a question?
Lauri.
Yes, I wondered if anybody else had listened to Bob McDonald's Quirks and Quarks on Saturday, because this was kind of one of his first things off the
He scooped me.
Sorry?
He scooped me.
Yeah, he scooped you. I'm sorry. But the other thing, the really cool thing that he did was they put this resonance on for music. And so they put these planets on, so they each made a sound, and they were able to show that when they got around and were kind of in that resonant pattern, then you could hear the pulses when they all were all kind of going around at the right time, and it produces this beautiful music.
I heard it on YouTube and I was going to put it on, but I know there's some gimmick you have to do to make the Zoom hear what's playing on your computer. So if somebody is clever and bored during this session, see if you can find it. It's like a 3-minute Zoom, YouTube.
Yeah, but that was.
It does sound really cool.
I know, yeah, like, so I mean, the whole idea of music and math.
Oh, this
All
whole music of the spheres, what I was thinking is there probably are real notes that correspond to these ratios, and I wonder what the chord is that this planetary system is playing.
Yeah.
You need Bach to tell you.
Anyway, people can look that up, yeah.
Okay, Darren.
Hey, can you guys hear me?
Yep.
Okay, perfect. Yeah, this question might be a bit silly. I came a bit late, so I wasn't able to hear or know what was the designation or the ID of the star and what catalogs would it be in. I'm just trying to understand more of the catalogs and learn more about like
Okay,
where.
yeah. So this is a big deal. There are all these different star lists out there. The Henry Draper, the HD list, is the list that was made in Harvard in the early part of the 20th century. And it's of all the stars down to something like magnitude 10. And it's if you see an HD number, it means it's a pretty bright star. By astrophysical terms. Right. But then there's all these other lists, and if you just look up HD 110067 in Wikipedia, then you see all these different catalogs. But you know, even the Gaia telescope has 2 billion individually identified stars in its list. Right. And I just boggles my mind.
How many are in the HD catalog? Do you know?
I think it's 2 million.
Okay, yeah.
It's big enough that it wasn't actually digitized until like the 70s. It was there was some problem, and so nobody. Well, I guess they didn't need to digitize the things until the 70s. That's when computers really came in.
And would those catalogs also have the planets? How you were talking about this recently, or just now? Would they have a designation for the planets, like the lettering after it as well in those catalogs?
Well, yeah, you put a BCD for the planets now. That is, but that's only since they've started seeing exoplanets.
Yeah.
So this is really new. I think it's Miles and then Margie, or is it the other way around?
No, it's order.
Miles.
Yeah, I remember when they were still debating over there were exoplanets. I always thought it was so ridiculous. But how can all these big planets fit in between the orbit of Mercury and its star? I mean, is this a normal thing? The planets that size can be that close?
I think the deal is they're looking with tests at so many stars. It's the very few that it's observation bias that tests will only discover exoplanets that eclipse the central star. And so those are the ones that you find. They're a vanishingly small proportion of the number of stars. And then they do these statistics, and now they think most stars have planetary systems around them, they figure. Because they know how many have them within this very, very tight angle range. And so then you multiply them by all angles, and you realize that it is as common as dust. Margie.
I don't know whether this is, am I on? Yes. I don't know whether this is of what you speak, but this is the December Astronomy magazine. And I haven't read the article yet, but on page 24, it's talking about exploring harmonics. So the article itself is called The Soundtrack of the Universe.
Cool.
And the exploring harmonics looks like that.
I love it.
And the idea is, it says, take a moment with the piano in a quiet room, find middle C, and an octave below middle C, and that's pressed down softly on middle C, so the hammer does not strike the piano string. While keeping the key depressed, play the C an octave below it as a short staccato note, and listen carefully for the first overtone. So these would be, I mean, you know, musicians know about overtones. So these would be all the overtones of that.
And any brass player knows these because that's how you make the different notes. With
Yes.
your embouchure, you'll hit these different harmonics. It like you can't play a trumpet without knowing your harmonic series.
Yep.
But yeah, these
Astronomy magazine.
it's the sort of thing that Archimedes was so sure of the music of the spheres. When he figured out about musical harmonics, he figured that that's how the universe must also be working. And anyway, that article cannot be about this particular system because those 150 authors and anybody that they talked to was sworn to secrecy until Thursday morning. That's how our embargoes work. I have a friend who is a science journalist, and she gets all the news ahead of time. Like she's on the list, but if she ever told anybody about what she sees, then she would lose her permission to get the early view. But you can see that science article, which came out that morning, they had interviewed the author, they interviewed other people to talk about it. They all know about it ahead of time. So maybe these journalists knew about it, but they weren't allowed to write about it in this article.
I have a question, Randy.
Yeah.
So the you mentioned the orbital velocities. Is that measured by looking at the star wobbling back and forth? Is that how they're inferring it, or how do they?
Yeah. Yeah.
Okay.
So you get a little bit of an estimate by looking at how long the eclipse is, but it also depends where it is on the disk. You know, they don't all go right across the fattest part of the star. So it is by looking at the, so let's just say it's a two-body system, okay, because that's a lot easier. They orbit around their barycenter, the center of gravity. So for the Earth and Moon, the barycenter is 2,000 kilometers below the surface of the Earth, or 4,000 from the center of the Earth. The Moon doesn't orbit around the center of the Earth. It orbits around the center of gravity. And the Earth is actually wibbling back and forth. And so somebody on Mars looking at the radial velocity, how fast the Earth is moving towards and away from Mars, would see this monthly wibble because of the Moon. And they would be able to work out the mass of the Moon from just looking at that. How you do it with 6 planets?
Yeah, that's where I was kind of, that's a lot to untangle.
And, you know, the stars aren't constant either, you know, so it's pretty wild.
Excellent. Looks like
anyway, I had fun
are...
with this, and I'm glad I had the opportunity to prepare this for you all.
Thanks, Randy.
Okay.
So, Lauri, do you want to speak to a couple of things that
Sure.
FDAO related?
Yeah. So we have launched our campaign, our fundraising campaign, which we are in quite a lot of need. So we're hoping that if anybody's got a few extra pennies, they might want to put it toward our FDAO funding. We are having a pancake breakfast on Saturday morning. Anybody that was up at the eclipse knew that we had fabulous waffles and everything that were being prepared on that morning, and we're going to do another fundraising, I think, on Saturday morning from 9:30 to 12, and we're making pancakes and we're having programs and children's programs and family things, and doing some fundraising there. So you are very welcome to come. I don't believe that it's going to be beautifully sunny. I don't think for us to put out our solar telescopes, but if there is any chance, then the solar telescopes will come out and we will show people a little bit of the sun. And then on the 16th of December are going to be the Saturday that's kind of closest that we can use to the solstice. So we are having our star party will actually be 6 to 9. We did this back a few years ago as well, is just because it is quite close to Christmas and things, we decided that we're just going to have 3 hours and it's going to be 6 to 9. And we are going to be continuing with our little fundraising thing that we're doing with Pluto. And what we're trying to do with the fundraising is that we're seeing whether or not we can raise enough money to actually kind of go all the way around Pluto. And even if we could even get twice around Pluto, that would be absolutely fabulous. So every dollar earned is a kilometer. And I am personally sponsoring Don Moffat, who some of you know. He's a runner. And so every kilometer that he runs, I'm sponsoring him. And I've roped my son into doing something down in Seattle at the same time. So I'm kind of doing a fundraising thing for him. Anybody is welcome to kind of to try that. And all of that money will be going towards kind of our school programs and things like that to keep our school programs going. So on the 16th, what we're going to be doing is continuing that Pluto theme. And we are going to be having a debate. And so there's going to be a debate that says, should we continue to have Pluto in as a planet, or is it going to continue as not as a planet? And we know what the scientific things are, but we're going to kind of just do a little bit of a fun thing for kind of the like general audience, the kind of the moral side of the whole thing and things. So we've got Alex Cowan is going to be on the pro side for planets, and Ruhi Mohammadjar is going to be on the keeping planet Pluto as an exoplanet, and we're just going to have this lovely debate. And it's going to be quite fun. I mean, it's on the silly side, but that's exactly what we're trying to do. And then we're going to have a little bit of some solstice stuff going on as well. And if it's a nice night, we're absolutely going to be putting up telescopes. I mean, they can go right up at 6 o'clock these days, and show people what's out there. Let's hope that it's a really nice night for that night. So RASC people are very welcome to come up and help out without any problem whatsoever. And we do encourage you to help us out in any way that you can. So the other thing that I have is that we've just about sold off all of the calendars and the almanacs and everything that we did get from National. And I still have about 3 calendars that have not been spoken for and about 3 almanacs that have not been spoken for. So if anybody is still interested in getting those, then please just let me know. I also I do have some workbooks for the explore the moon, both with binoculars and with telescopes. And those I'll just keep those until they are paid for. So the almanacs, unfortunately, are $17 this year, just because of shipping costs, and the workbooks are $12. So, and the calendars are still $15. They're still there. So if anyone is interested, please just either fire me an email or just put something in the chat and I can get something to you. If there's anyone that I have not got if you have not got something that you already have pre-ordered from me, would you please let me know? Because I'm thinking that I know a couple of people that still need things, but I'm kind of down on my list. So I'm hoping I haven't forgotten anybody. Okay, I think that's it. We're still kind of looking at venues and things for the kind of the social event at the end of February for our like post post general meeting, our annual general meeting, and still looking for things that work. You know, in some cases, things are too small, or things are too large, or things are too expensive, or they, you know, don't take, we wouldn't be able to do a presentation, or all different kinds of things. So it's a little tough to find everything, but we'll still continue to look for that. And we'll let you know as soon as we've got something. Thank you.
Thanks, Lauri.
Yay.
I don't have anybody else on the list. I was just wondering, I know David Lee is on the meeting. I don't know if he has any SIG related announcements or anything.
Yeah, I do actually. So the beginner's SIG is tomorrow night. Originally we had Randy scheduled to tell us about the moon, but we'll have to delay that until next month. So in lieu of that, I was thinking today about what to do, and I know a lot of the beginners group, we have a lot of new members in the beginners group, and a lot of people have been asking about observation type tools. So I thought I would go through my collection of atlases, planetarium software, and planners. So 3 different kind of categories for either, you know, observing or imaging, and what's appropriate for a beginner, and what would be appropriate for intermediates, and etc. So we'll talk about those. I've got a pretty big collection from beginners to more advanced books. So yeah, we could probably talk about that tomorrow night. And any other things, like if people have been observing, like I know that we've had a few clear nights. They haven't been totally rained out. So that would be great. And yeah, I hope to see everybody there. If you're not part of the beginners group and you would like to be, let me know.
I'm really sorry this trip came up to go to Vancouver and I can't get out of it.
No problem. We will be waiting for you in January.
Hey, I bet Chris Gainor has some Hubble news for us.
Yes, I do.
Oh, there he is.
But I'm going to transition a little bit from Lauri's presentation with this thing. Just a second. Last night, Audrey and I were down in Victoria to see a show, and we stopped at the the name is just gone out of my head, but there's this chain of burger places in Victoria, and there's one at the Gateway Mall. And on one of the walls I found this.
Nice.
So the observatory is kind of part of the local landscape. So I'm sorry I've forgotten the name of that chain. They have one in Cook Street Village, and Big Wheel. Big Wheel, yes. And I think they have one in Langford, but this is the one in the Gateway Mall, you know, sort of near Saanich City Hall and all that. So anyway, I thought that was kind of neat. So Hubble. So last week, word came down that Hubble is having some gyroscope trouble, and they're still working on it, and so its activities are suspended a little bit. So just kind of by way of an explanation, Hubble has 6 gyroscopes on board, which basically tell it which way it's pointing, and that input is important for it to aim itself. And now 6 is more than enough, but 3 have failed, and it's kind of an interesting story, because they during the early years of Hubble, gyroscope failures were a regular occurrence, and they before one of the servicing missions, they were down to one gyroscope, which is not really that good a place to be. But well, when that happened, they began to work on, well, how can we make the most of this situation? And so some of that work will probably eventually be useful again. So what the reason the gyroscopes fail is that there's sort of an electrical line from the gyroscopes that have to go through some oil inside the gyroscope, and it's just, you can't avoid that. And so finally, just before the last servicing mission, which is 14 years ago now, they decided to create a set of gyroscopes that where these wires were coated and would therefore last longer. They wouldn't be so susceptible to this corrosion. So and they were able to do that for 5 of the 6 new gyroscopes they intended to install in that mission. So what happened is that the gyroscopes came in packages of 2 that they would replace. So they replaced 2 of the 3 sets of 2 gyroscopes, and one of them was the one that only had the one new type of gyroscope. So they were already down one gyroscope, and then it was time to replace the 3rd set of 2. And what happened is that they put in the new gyroscopes, and they couldn't get the damn thing to fit because there'd been a wee bit too much insulation put inside, and it was too tight to fit in the spot. So they actually had another replacement set of gyroscopes, but they were the old type. So anyway, when the astronauts finished that final servicing mission, they replaced all 6 gyroscopes, but only 3 of them were the new type that would last longer. And it's interesting because this was barely noted in any of the coverage or announcements about the spacewalks and everything else. And I knew about that this had happened, but just to sort of get it all tied down for my book, I really had to dig around to find that. It was basically ignored, even though that could be deciding Hubble's future. So anyway, by 2018, 5 years ago now, all 3 of those old types of gyros had failed, and now one of the newer ones is starting to fail. But anyway, they're quite confident that they will get Hubble back to work, and they say that they can continue to use Hubble even if they don't have only one gyroscope. Now, what that means is that if you only have one gyroscope, there's some activities that Hubble can't do, and that's mainly things within the solar system where you have things, planets and asteroids and comets and what have you, moving relatively fast relative to Hubble, and you just need more gyroscopes to help you know where you're going. So we'll see if they can figure out the issue with this one gyroscope and then restore it with at least 2 gyroscopes and hopefully 3, and then Hubble can get back to its regular programming. But I suppose it's possible that something else may fail, like an electrical unit or something like that, and that could knock Hubble out of operation. But the worry has always been the gyroscopes, and this is coming up again. Now, when they launched JWST, the NASA was hoping to get at least 2 years of joint operation of the two space telescopes together. We're actually getting close to that. I mean, well, let me think about that. We're over a year, so I guess next summer we would have 2 years of joint operation. So anyway, we'll see how that goes. But of course, everybody's hoping that they have more joint operation than just the 2 years, because the telescopes Webb and Hubble look at kind of different wavelengths, so they can image similar objects and get a bigger range of wavelengths from the objects they're looking at. So anyway, that's my report on Hubble.
Did you have a question, David?
Yes, I did. Chris, it sounds like these gyros are kind of the Achilles heel of Hubble, but are there other things that could go wrong? I mean, is it unrealistic to think it'll go another 10 years?
Okay. Well, of course, this begs the question of how long is Hubble going to stay in orbit? And right now, or at least when I finished my book, the best guess was that it would stay up until 2036. However, if the sun starts, blazing a bit more than usual, that could mean that its orbit decays at a faster rate, which is what happened to Skylab all those years ago. Its orbit decayed faster than they expected. But there's all sorts of things that could go wrong. They are careful using some of the imaging equipment, because the chips in some of the cameras don't last forever. So they keep a very close watch on how much they use various cameras and imaging equipment on Hubble. And then there's just things like what if the batteries fail? There's power units, and I think a year or two ago there was a problem with one of the power units that brought Hubble down. I'm sort of saving all this stuff in case I ever get asked to write a second version of that book. But I've forgotten some of it. But that was a problem they had a year or two ago.
Mm-hmm.
Or let's say the computers fail or something like that. So they're
well, they
Hubble is healthy, but
I'm certainly, when they designed it, there was certain levels of redundancy that were built right into it, right? So that's why I was just wondering, as the layers start to die, you get you kind of run out of the redundancy, right?
Yes, and actually there's another thing there's another issue that's coming up too, which I was going to mention, and that's to do with that good old bugbear, budgets on Earth. You might notice that certain elements in the U.S. Congress are very big on lowering spending, and this is one of the issues that's come up when you hear that, oh, they're going to shut the government down, and this is usually some very hard right Republicans wanting to cut spending. And because NASA is considered to be discretionary spending, whenever there's cuts in the U.S. budget, you can rest assured that NASA is going to feel it. And so there's actually been some discussion about cutting the astronomy budget at NASA, including Hubble. So that, you know, there's a discussion going on about sending up well, this is another thing which gets to the whole matter of when Hubble comes down. The years ago, the government passed a law basically saying that Hubble could not make an uncontrolled reentry, that there would be an attempt made to attach a vehicle that could, you know, fire a rocket so that Hubble would enter the Earth's atmosphere at a predetermined spot. They didn't want another situation like Skylab. So that's all well and good, but they actually haven't built this thing. I think a few months ago, NASA ordered a study into this about getting a private provider to look into it. And so far there hasn't been any announcements about where they might go. Apparently they've got bids from 8 different companies, but only a couple of them are known to the public, and I've never heard of these things. But anyway, that would involve a bunch of money, and there was just a discussion today about, well, if they're going to go to all the bother of sending something to change Hubble's orbit, well, can they do repairs on Hubble? And now the problem is that the shuttle was the perfect platform to do that, and spacecraft available today are not half as good as the shuttle. But somebody was arguing, well, you know, miniaturization is more advanced today than it was, you know, 15 years ago when the last servicing mission, 14 years ago when the last servicing mission went to Hubble. So anyway, that discussion goes on, and you know, along with the discussion about cutting budgets. So we'll just have to see. But yeah, there's always something going on with budgets at NASA. The other thing that's going on right now is there is a plan to bring samples back from Mars with a robotic spacecraft, and they're discovering that that's a bit more difficult than they thought and more expensive. And so that's a big topic in Washington because there's concern that if they proceed with this plan for Mars samples, that the cost of that will eat up other parts of the NASA budget. So yeah, then NASA isn't the political football that some things are, but there's still no shortage of politics, unfortunately.
Hey, thanks, Chris.
Chris?
Yeah.
I'm curious what the function of the overlap between Hubble and Webb could be. Like, what sort of things are they observing together that is different than just a Webb then later on looks at things that Hubble has already looked at over its 30 years?
Yeah. Well, I think, I mean, it's the main reason is that they observe in different wavelengths, and you know, Hubble has optical wavelengths which Webb doesn't have. I think even some near infrared wavelengths that Webb doesn't have. You know, Webb's are kind of deeper into the infrared, and Hubble also has some near ultraviolet wavelengths that it observes in, and so I think you know, for example, they're looking at kind of the priority things, which are, you know, very distant galaxies and other objects like that, and also exoplanets. you know, I think those are the two big priorities. And because those Hubble and Webb are useful to you know, once an exoplanet has been discovered, they aren't used to discover exoplanets, but once there's interesting ones discovered, then they can be aimed at them, and they can figure out, well, what's the chemical makeup and things like that. And you know, it could be that one of these, you know, the big thing is trying to find an exoplanet that resembles Earth, and you know, so after, you know, some of the earlier work done by, you know, some of the telescopes you were talking about in your talk, then you know, Webb, with perhaps some help from Hubble, could you know, tell us what these exoplanets are made of, and what they're up to, and whether anybody's waving back at us.
Thanks very much, Chris. Anybody else with questions for Chris? Okay.
Yeah, I'll just say one thing, of course. About a month from now will be the big meeting of the American Astronomical Society, which last year was in Seattle and I went to. This year it's in New Orleans, which might be a nicer place to go, but it's more expensive. But anyway, there will be a lot more announcements coming out of there. So we'll tune in and see what we get a month from now.
Thanks. Does anyone else have any interesting things to share with the team, or any other questions? Okay. I don't know if anyone else has any images, but I have a couple over the past month or so that I've managed to acquire. Dave might have a few himself, Dave Payne. Why don't you go ahead, Dave?
Oh, and Brock, one more thing we should talk about last week, because some people weren't here, but that was really, really jolly. So
why don't we start with a recap of that? Because I was curious myself. I wasn't able to come in, but
do we have a count of how many people were there?
Not accurately, but about 40.
Wow.
We had 40 in this little room.
Wow.
And it was delightful. There was a real buzz. There were old timers and there were newbies. There were several people came for the first time. There were some spectacular pieces of equipment, and there was some nice simple things. And so there was a lot of just yammering and you know, being delighted that we were all together. But then we kind of shut everybody quiet and then get individuals to talk about things that they had. And one thing that was really good is that Sid was here with all sorts of things. He says, I'm not going home with this stuff. You pay me whatever you want. And I don't know how it happened, but I came home with a second Omcom telescope. This is the same telescope that I normally use every day. He convinced me to take this other one, but it has a really, really nice mount that somebody from Vancouver did a really beautiful job working on. And I'm just fixing it up now. But there was some great, great bargains. Is anybody?
I got a chair.
You got a beautiful observing chair, yeah.
Yes, but no, but I don't know whether you saw it because he made it. He made it, and
He
then
made
there's
it.
another one that somebody had that was a professional kind of thing.
You got the one from Doug, right?
Yeah, I did.
Yeah.
I did. I have to take it off, like clean it up a bit, but it'll be really nice.
It was super. And oh yeah, and I got a little tracker from Dave.
Yeah.
People, say, I've got a bigger, better one. I'm getting rid of this one. And yeah, and then I also came home with a big mount from Reg. So Eva's not happy with me, but yeah.
Randy, I'm glad you mentioned the tracker because I was just curious. I think a lot of people have trackers, but they may have bought them and just never got around to using them, or they may have didn't quite get them to work properly. I'm just wondering if there's an interest in the center to have a little workshop. We could get all the trackers together and iron out whatever bugs need to be ironed out.
Like get together a Kettle Point thing or up on the
Cattle
hill.
Point, or maybe up on the hill, whatever we like. Anyways, I'll put something together and just see if people are interested in doing that. Because I know a lot of people were not fully understanding of how to get some of them to work.
Great. Thanks, Randy, for the recap.
Does anybody else want to talk about last week? Anyway, 40 people in this room. It was cozy.
I bet.
Now I'm having coffee. Not today, but.
Oh yes. Now we're gonna do coffee now. So you should come here.
I think Reg set you up for that amount too, at a price of $125.
Excellent. Okay, Dave, why don't you share?
Sure, Brock. I'll just share my screen here. So I only have one.
Wow.
One new image to show. I do have a whole bunch that were taken during the summer. This one was actually recently taken. It's in November. It's of the star forming region known as the Monkey Head Nebula. It's a sharpless 252 object. And it's taken in the Hubble palette. It's false color, so you wouldn't really see it in exact these colors. But the colors do have meaning. And I went for this target. It's really hard for us to take Orion because from this location, because it's usually raining in the wintertime when Orion's up. And for this subject, it's actually often neglected object in the sky because although it's in Orion, it's got huge competition for cameras, right? So I decided to go after this one that's spectacular in its own right. It's actually not part of the Orion complex. It's actually molecular cloud complex. It's actually 5 times more distant, further along the arm than the Great Orion Nebula. So it's actually quite a big object compared to some of the ones in Orion. But I liked it because there's lots of details on what's going on in the gas clouds.
That's
now,
spectacular.
I haven't got any other images to actually show finished images, but I was working quite a bit last couple of days on another image. This one's in Cassiopeia that we actually have lots of opportunity to image. And that's of the Bubble Nebula over here and the Lobster Claw Nebula over here. And it's the same palette as you saw before. And I actually used a technique that can give you greater detail on certain images. So I've got a lot of detail in this image that I'm still working to pull out. But you can see how much resolution there is in these images. And partly to horrify observers with the photography, but I just thought I'd take like 3 minutes to show how we actually create these images with the colors and balance and the whole thing. And the way we do it is we kind of cheat. So what we take out of the camera is this is a normal image of the same area taken through red, green, and blue filters. And what you're seeing showing up in red is the emissions from hydrogen. You're not seeing a heck of a lot else, partly because the emissions from the other ions that are present is much weaker, and partly because there's so many stars in the way. So what we employ is one of these scary artificial intelligence techniques to get the stars out of the way and use filters to get our combined image. And this is what is sort of the precursor. On the left is the precursor to the image on the right. So we take out all the stars and use our special filters to bring out all this nebulous material. And what we do is, you can see it's a lot of green in here. There's a little bit of blue. So we apply some color correction to this image to get the colors we want. And we also extract the brightness from this image to get the details that we want. So for example, when we correct the color image for the Hubble palette, we get much more pleasing and using much more of the spectrum, far less greens, more reds and yellows and blues. So we can get the color from that. From the lightness, now the lightness is a monochrome image. We actually work on the lightness image, and I don't know if you can tell over the screen, there's actually a lot of detail, darks and brights and contrast in that luminous image. And we can do that. If we did that, tried to do that, bring out that detail in the color image, we totally mess up the colors. So we extract the lightness, we work on all the details using Fourier transforms and other such local contrast additions and sort of thing to get the brightness right. And then we recombine the color with that luminance, so we get the best of both worlds. So here's what the color image is, and then when we combine it with that detail brightness with much more contrast, we get the colors we want. Now, this is a starless image, and some people like starless images. I don't like starless images because they're fake. They're too unrealistic because there's stars everywhere. And all these emissions are ultimately caused by the stars. So what we do is we take our original red, green, and blue image, which has the right star colors as we would see them. We extract the stars and leave all the non-star material behind, and including, you'll see a couple of clusters in there. And then we add it back in to the detailed nebulous image to get our overall final image. We can control a little bit independently how bright the stars are relative to the nebulosity, and that's really pretty much to taste. But I just thought I'd spend a couple of minutes so you can maybe appreciate a little different way when you see these images of what's going on and how they're put together.
That's
David.
fantastic.
David, you refer to the initial reds as being hydrogen. Is there ionic significance to any of the other colors?
Yeah, there's a great significance to it. So it's a little bit complicated, but it is extremely interesting. The blues are emitted by oxygen, and it has to be fairly rarefied oxygen ions. And oxygen really likes its electrons. It's a great oxidizer. It loves electrons. So it glows blue when it's not too dense, but it's got to be there. So if it's too sparse, it won't show. And it's indicative of being hit by very strong UV radiation. So the next colors that you see are basically green running through yellow and into orange, and that's the red hydrogen alpha signal. And its reason it isn't red is because we assign it to these other colors. Red gets assigned to sulfur, which again only emits when it's fairly rarefied, but it differs from oxygen because it's just ionized. It doesn't really care for electrons one way or another. So it only takes weak radiation to ionize that and make it glow. So you usually see next to a star, you'll see an area of blue, and then, or in a star forming area next to a cluster, you see an area of blue, you see an area green going to yellow as the sulfur increases, and on the outer edge, it turns sulfur red.
Thank you.
Very nice.
That's fantastic.
Thanks.
That was wonderful, David.
Good. Glad you liked.
I have a couple of pictures I'll share as well, but I don't have any interesting spiel about them, but have a look.
Quick question for Dave while you're pulling that up. How long did that take you to compile all of those photos? How much processing time to create your final image?
It would take, one of these ones would take me 6 to 8 hours of work, and maybe 3 or 4 nights of worth of images.
That's quite an investment in time.
Yeah.
The rest of us about 3 or 4 times that long.
What was that, Gary?
It would take the rest of us about 3 or 4 times that long to do your process. That's for darn sure.
This picture here is not as much work because it's in color. I have less time at this point in my life to dedicate to the Hubble palette stuff. So, but this is just a more of a true color image of NGC 1333, which I like because of the fact that it's kind of a nice mixture. It's got reflection nebula, which is just gases that are reflecting the light from this really bright star, but it also has it's got some dark nebula, which is some really opaque dust and gas, and it's also got some young star forming regions in here from the looks of it, which are emitting hydrogen alpha. It's like Dave was talking about, there's hydrogen gas that is excited, and this is in the true color, so you're seeing the hydrogen as its original red appearance. So it's kind of an interesting region. Lots of texture.
Brock, what was the object name?
NGC 1333.
NGC.
It's in Perseus.
Okay.
Brock, what is the little object that's just to the left of where your cursor is right now?
This here?
Right there. Yeah.
I don't know. It almost looks like it's a region that's being lit up.
I think it's a
by a
reflection
star.
nebula.
Yeah.
I've seen. I don't know if this is the one that everybody shows, but it looks like a fan.
Yes.
Yeah.
But I don't know if this is the one that everybody shows as the fan. Or there may be another one that looks just like it.
Could be. But
Yeah,
yeah, it does look like that.
it's a red star, and that's why the reflection there is that orangey color.
Yeah.
And then the brighter star, its reflection to in the center of the image is more blue.
Mhm. And then the other picture that I had is the Cocoon Nebula, which was also, this was actually quite, both of these were done without any filters, but it was during the previous new moon that we had, when we had a bit of a clear run, which was kind of rare for November with the new moon. So this one, again, no filter. So this is just best attempt at what it would truly look like in true color. And I've seen the Cocoon before and I've done it before myself, but I didn't really have enough exposure to really show this huge region of dust and gas around it.
Yeah, nice job on the dust and gas.
And then there's also a bunch of background galaxies if you really look closely. So it was a nice, fun one to image.
What's the number of seconds in the field of view here? I was always surprised to see so many other stars in the background. Is that because the majority of the stars that we're seeing are well beyond the actual nebula, or there's probably a few in front?
There's a few in front, but vast majority are behind it. The gas is blocking quite a few, because if you look in the corners, there's a lot higher star density than there is towards the center, which is kind of indicating that those are background stars in behind that gas region. But it's taken with my big telescope, so I don't know off the top of my head what that field of view would be. But it's a pretty small object in the sky. It's pretty big in reality, but
yeah.
But again, it's the red section in the core of it would be all hydrogen gas, and excited probably by that central star, I would imagine. But so, anyways, that's all I had.
Awesome.
That was a polite name for that, for what that looked like. What was it called again?
It was the Cocoon Nebula.
Cocoon Nebula. Yeah. Okay.
It's just
Lauri?
I just was somebody just put in the chat about how Dave's last picture reminded her of something else that she saw, and I did not get who it was that was talking or in the chat saying that it looked like a woman. It looked like a woman's face. David, can you put up your last picture again?
Oh, okay.
That's quite the imagination. I didn't.
Yeah.
Be careful what you say.
Yeah.
I'm sure they're all Rorschach tests.
All I'm going to do is I'm going to
like I noticed the person's face. Like above the blue to the left. So I don't know about the other stuff, but I noticed it right away, was the face. Myself.
Well, I don't know if I pulled it up or not.
Yeah.
I think you're looking down on a young lady sitting on the ground. Her legs are out to left and right, arms out to the middle, and the dog's in the middle of her hands.
Were you talking about the original one I showed, the monkey head?
The lobster claw.
Oh, the lobster claw. Okay.
No, it was just the last picture you showed.
Okay, Susan, you can explain it.
This one.
Yeah.
Yeah.
Well, this is the bubble nebula because it's got a bubble in the middle of it. This is the lobster claw, which, okay, here's kind of a claw, but I'm not seeing. Maybe this is a snowman, the top of a snowman.
Susan, can you describe where the head is?
Oh, totally looks like a little case.
Yeah, so there's two where on the left-hand side, there's the blue, bright blue area. And at the end of that is a hand connected to the other arm, which is sort of a brownish, yeah, more down
Over
there.
here, two arms connected.
Yeah. So
Yeah.
she's sitting there and she's got short hair and no glasses as far as I can tell. And then on the right-hand side, oh, I see another image. I see all kinds of images. So I don't know how to tell you. In the right-hand cluster of color, there's a bluish area.
Here.
Yeah, so that's a dog's nose. And above it are two eyes, and then it's got two floppy ears.
Oh, I see.
Oh,
that.
I see it. I
Yeah.
see it. I see it.
I see that.
I see the ears and everything.
Yeah.
I need to work on my pareidolia.
Anyway, I just see all kinds of, it's just interesting how the human brain wants to see and make form out of things. And so.
Well, this
This
one,
one, Susan.
this one's the monkey head, so it's got a mouth.
Oh, yes.
There's got a mouth here, and there's like sort of a round, chimpish sort of chin, and a very flat nose, and then this prominent brow. It's kind of face down. But
when I see something
I don't
else.
see that at all. Yeah.
yeah, you could. It's like looking at clouds sometimes, right?
It is, yeah.
Yeah.
And the other picture that I'm sorry, I don't know people's names yet. Brock, I think you showed a sort of a picture with a dark column, I think. And it certainly looked like some sort of TV version of an alien.
I just wanted to let you know, Susan, that I saw the face right away.
Oh, yes, you mentioned that.
Yeah. So
well, since I understand virtually nothing of the scientific stuff, I tried to absorb that, but just use my eyes to see what I saw.
Well, we are programmed to look for faces, right?
We are, yeah.
But it's also one of the things I love about this amateur astronomy community is we have something of a common sense of purpose, and we also have our own personal interests and views, and I think it works. It works for me. All the variety of things that hold us together, despite all the different backgrounds and experience and interests, and this is part of what I love about the amateur astronomy community.
Yeah.
Excellent. Is there anyone else that has anything to share or discuss?
I had a question. Maybe it was when I wasn't part of the meeting. Is there a night out or a night at UVic this week? And if so, is there an agenda or presenter?
It's next week.
Could I speak to that? The next, we have speakers on the second Wednesday of the month at UVic. The next speaker is Dr. Doug Johnston, and Dr. Doug Johnston is an excellent presenter, a very entertaining fellow, and he's going to be talking about a thing called the far infrared satellite that he's trying to promote the construction of, and he calls far infrared astronomy the science of the cold, the bold, and the dusty. And it almost sounds like the title of a spaghetti western, but he will make it a most worthwhile trip out there to hear him speak. He's a great speaker. And so that begins at 7:30. on the 13th, Wednesday, the 13th of December, in a different room this year. This time it's in room B150 or Fleury Hall. It's a very much larger place, so we need more people to fill it out. So please come out.
Bring all your friends. Yes, yes.
Same building?
Yeah, same building.
And can I say to please do not go in the other room? There's an exam being written at that time.
P104 is the exam.
Yes.
Yeah, okay.
Alex, should we put up a sign on the door just to remind people again?
Maybe that might be a good idea.
Can we just put a sign saying, you know, RASC, please do not go in, go to B150? Yeah.
Yeah.
Exam in progress.
Because automatically people will just kind of go in and start opening the door and they won't know. So,
Right.
Yeah.
Okay. Sounds like a good speaker.
mhm.
Excellent. Anything else? No? It's been actually a good evening. Lots of things have come up. If there's no one else, I think we could call it a night.
Thanks, everybody.
Take care.
Thanks, Brock.